In this second video on channel flow, we're going to take one step further, take the equations that we worked out in the first part from force balance and from talking about the relationship between stresses and velocity gradients. We're going to take those two equations and we're going to solve them explicitly to figure out what the shear stress profile looks like through the fluid and what the velocity profile looks like in the fluid. So last time we set up the problem that looks like this. We had an element of fluid that we're pulling on. The fluid is flowing from left to right, shown by the black arrow on the right. And there's a pressure gradient, high pressure on the left, low pressure on the right. And there's a plate on the top that's connected to the fluid. There's a no-slip boundary condition there. So as the plate moves, so does the fluid. They're connected together. There's no slip between the two. And the coordinate system is shown in the upper right-hand part. And what we want to do is figure out now what is the velocity profile and what is the shear stress profile in this channel. So here we take our little element. We did a force balance on that element last time. And we came up with some expressions for the velocity and the shear stress, but we have to apply some boundary conditions now to make sense of those. So we have two equations, and we're going to talk about what the boundary conditions might be so we can make use of those equations. And here's where we go. So here are the two equations that we arrived at last time. Equation 1 came about from a force balance, sometimes called Stokes' equation. And equation 2 came about as a description of what a Newtonian or a linear viscous fluid looks like, with relating the shear stress through the viscosity to the velocity gradient. So what we're going to do is we're going to take equation 2, the shear stress term, and plug it into equation 1, which shows the derivative of the shear stress. And now we'll have an equation that relates the velocity in terms of the pressure gradient. So let's start there. I'm going to move back over to the other screen. We'll do a bit of math, and then we'll come back and we'll have a nice expression for the velocity as a function of position and the shear stress as a function of position. Okay. So if we put equation 2 into equation 1, we end up with the expression that the derivative of tau with respect to x2 is equal to the derivative with respect to x2 of the viscosity times the velocity gradient. And remember, d tau dx2 is just equal to the pressure gradient from our force balance, so this is just dp dx1. So now what we'd like to do is to integrate this expression. So let me take the latter two parts, and we'll write it as, take out the viscosity, it's constant, so it can come out of the derivative, times the second derivative of the velocity in the one direction with respect to x2 is just equal to the pressure gradient dp dx1. So let me take the mu to the other side of the equation and write the derivative of the velocity as the derivative of the velocity with respect to x2 times the derivative of the velocity in the one direction with respect to x2. And I have 1 over mu on the right-hand side times the pressure gradient, dp1, or dp, no 1, sorry, with respect to x1. I can now integrate, and if I do, I end up with the integral of d dv1 dx2. I take the dx2, put it on the other side. That's just going to be equal to 1 over mu times the pressure gradient, dp dx1, times integral dx2. And if I do those integrals, I end up with, on the right-hand side, the velocity gradient, dv dx2, is equal to 1 over mu dp dx 2 times x2, and then plus I need to have an integration constant C1. Okay, so I can right away, I can get a bonus out of this. I can calculate the shear stress. Remember that the velocity gradient from the earlier equations for viscous flow and Newtonian viscous material is just equal to 1 over the viscosity times the shear stress. And so implies that the shear stress tau is just going to be equal to the pressure gradient times x2 plus mu times c1. Okay, so now we have an expression for the shear stress as a function of position. If we can solve for c1, we'll be home free. So we're going to call this equation 3. And now we're going to integrate this equation one more time. We'll call this equation 3. We'll integrate one more time. Take our expression here, integrate that again, and we'll come up with the expression for the velocity. So let me take this paper away and start fresh. So now I have an expression for the velocity by calculating the integral of the velocity. It's just equal to 1 over the viscosity times the pressure gradient times the integral of x2 dx2 plus c1 times the integral of dx2. And if I do that, I get the velocity 1 direction as a function of vertical position x2 is just equal to 1 over 2 times viscosity times the pressure gradient times x2 squared from the first integral plus c1 times x2 plus the second integration constant c2. And I'm going to call this equation 4. Okay, and now to make some progress, we need to apply some boundary conditions to this. So let me move back to the PowerPoint presentation. So here's what we've done. We've inserted tau, expression for tau in equation 2 into the differential equation for tau. And we've come up with two equations, one that describes the velocity profile, the upper equation. For v1, the velocity is a function of position. And we have some constants in it that we have to solve for. And we have the shear stress profile with a constant C1 in it. And to solve for those constants now, we need to have some boundary conditions. What's happening to the fluid top and bottom? Okay, and so this is where we're going to end up. We're going to end up with an expression that looks as I've shown here by applying the boundary conditions. So let's take a look at how to do this. So the boundary conditions are two. If you remember our stream, we have a velocity at the top is equal to v1 in the one direction at position x2 equals 0. And that's some velocity, has some value that we can prescribe. It's the rate at which we're pulling on the top plate. And we know the velocity at the bottom at x2 equal to h. And we said we have a no-slip boundary condition, and the bottom is setting still, and therefore means that the fluid at the very bottom must be setting still, and so the bottom velocity must be equal to 0. So this is due to the no-slip boundary condition. So we'll call these BCs, boundary condition, and this is the top boundary condition, that the fluid is being pulled along at some constant velocity v1. And if we insert that information back into these two equations, we'll end up with expressions for C1 and C2. So if we apply the boundary condition at the top, the first boundary condition, we'll end up with, and we look at our equation up here, right? If we're at the very top, where x2 is equal to 0, that's velocity v1 at 0. And only thing that's left, this term is 0, the x squared term is 0, and so the velocity v1, the constant c1 must be equal to v1, the applied velocity at the top of the flow. And we apply the second boundary condition, that v1 at h is equal to 0. Plug it back into our equation here and solve, knowing c1, and we can solve for c2. I'm sorry, oops, sorry, this is a mistake. This should be c2. We get c2. When x2 is 0, we get the only thing that's left is c2. Now we apply the bottom boundary condition that there's no velocity at the bottom. I'll let you work through the math, but you'll come up with c1 is equal to minus the term v1 at the top plus 1 over twice the viscosity times the pressure gradient. And since we're solving for this at x equal to h, right, x2 equal to h, we get an h squared here. And then in the denominator of this whole thing, we have h. Okay, so that's what the flow looks like. And if we plug all that back in, we can go back to the PowerPoint presentation. We end up with expressions for the velocity that are shown here. The velocity depends upon position, vertical position in the flow, depends upon the initial velocity at the flow, depends upon the pressure gradient. And the shear stress, likewise, depends upon the boundary conditions, the velocity at the top plate, and the pressure gradient in the system. And one thing for you, Chris and I will emphasize frequently throughout the course, is you should make sure that this expression is dimensionally correct. And I'll leave that for you to work out. But it is dimensionally correct. But it's always smart when you derive an equation to make sure that the units on both sides of the equation balance out. Okay, let's look at flow in the general case that we've just talked about. We're going to have a situation where we have both a pressure gradient, high pressure on the left, low pressure on the right. Remember, it's negative because x-axis is increasing to the right, but pressure is decreasing to the right. And we're pulling on that plate at some velocity v1. And we get a fluid flow in the direction indicated by the arrow. We've applied the boundary conditions that are shown, and we end up with this general expression for the velocity and this one for the shear stress. And now we want to plot those so that we can see what the velocity profile and what the shear stress profile looks like. And let's see if they make sense. Well, I think they make sense. The velocity at the bottom of the flow in the lower corner down here is equal to 0. And it goes up to a maximum velocity and reaches the velocity of the plate that's being pulled. So I've implied a plate velocity of 1 meter per second, and the velocity reaches exactly that value at the plate. Okay, so that's the velocity profile. I can draw that velocity profile on the plate, so it's the velocity increase going from the bottom of the plate to the top of the plate. And I can draw the shear stress profile in the same way, cutting through the plate. And it's shown here in the lower right-hand corner that I go from a shear stress of -2 pascals to 2 pascals at the top of the plate, given the pressure gradient of 2 pascals per meter. Okay, so that's the general case, but it's really more interesting in a sense to look at the specific cases. In one specific case, I can set the velocity equal to 0 at the top and leave it 0 at the bottom. So I now have, this is like the magma being shoved between 2 fixed blocks of granite. And I end up with a parabolic velocity shown in the bottom, velocity profile shown in the bottom left-hand corner. If I drew that on top of my picture up here, it would look like that. So the velocity is 0 at the top and bottom, but maximum in the center. And the shear stress increases from -1 to +1 as I go from the top to the bottom of the flow. And finally, I can look at the case where I remove the pressure gradient and only have the plate moving at the top and the bottom. And the velocity then increases linearly from the bottom to the top. So it looks like that would be the velocity profile. And remember that the shear stress is the derivative of the velocity profile, so it must be equal to a constant. And that's what's shown here by the vertical line here. So the shear stress going through this flow would look like that. Okay, so those are some special cases that we can look at. And we can combine them all, and I'll leave this slide. I'll put the slides on the Moodle so you can have a look at them, but this is what the three look like combined. And what you can see fairly quickly is that the sort of general case shown in blue is just really the sum of the two. I'm sorry, the general case shown in blue is really the sum of the two cases, the red case, the pipe flow case, and the green case, the plate moving across the top. The blue is just basically the sum of those two situations. So to conclude, I have a test for you to think about, and something we'll talk about in class. Let's think about a case where we have a stream flowing, such as back here, but rather than pulling the plate, let's not prescribe the velocity of the plate at the top. So we're not going to prescribe that velocity. We're just going to say the plate is moving. It's like a river flowing, and you're in a canoe floating down the river. All right? And what I'd like you to do is to think about what the velocity profile through that stream should look like and what the shear stress gradient should look like in that system. So that's kind of your assignment. The velocity V1 is not prescribed. It's just, we're not going to impose it. We're just going to let the canoe float down the river. And we're going to consider the case where the top surface is what we'd call a free surface, so that we don't know what the value of V1 is at that time. At that point. So your assignment is to determine the velocity profile and determine the shear stress profile in that system. And you need to do is you're going to have to find a new boundary condition. And a good boundary condition to use in that case is to set the shear stress at the top surface equal to 0, because you're not dragging the plate across the top, so there's no shear stress. It's a free surface, no shear stress at the top. And use that as a way of calculating what the velocity at the top should be. And once you do that, you can bootstrap yourself to getting the shear stress. So think about that problem. We'll talk about it more in class, but give us some serious thought so that we can attempt to work through that situation in class.